Do a Kepler's practice problem. We're going to find the speed of a satellite in orbit 265 kilometers above the surface of Mercury. And we're going to determine the period of that satellite. Uh, so let's say we've got Mercury here. Let's make Mercury. Okay. And let's move him a little bit. And we've got a satellite that is orbiting Mercury. Here's the satellite orbiting Mercury. And it's orbiting 265 kilometers above the surface. Okay, so its orbit is 265 kilometers. So in order to determine the speed, uh, we would need the period. We technically need the period to determine speed because velocity is equal to, or the orbital speed, tangential speed, is equal to 2 pi r over t, the radius of spin. We have the radius because we'll be able to find from a chart what the radius of Mercury is. Okay, this is the radius of Mercury. And we'll be able to get that off a chart, but we still don't know the period. We don't know if it's synchronous, if the satellite's synchronous to Mercury, and we'd have to look up the spin of Mercury. We don't know that information, but we can derive an equation for the velocity uh, of any satellite, and we can derive that because we know that the force of gravity that acts on any object orbiting another, or a satellite orbiting a bigger object, is equal to the centripetal force. Okay, the force of gravity that that thing's experiencing is equal to the centripetal force. Uh, it is the centripetal force. Gravity is what holds this object in space as it orbits the planet. What does gravity equal? Gravity for the satellite, the force of gravity that the satellite's feeling, is equal to our gravitational constant times the mass of Mercury times the mass of the satellite over the radius between the Mercury and the satellite. So this distance here, this r, and that's equal to the centripetal force of this that's felt by the satellite. Well, that's also equivalent to the mass of the satellite times the centripetal acceleration of the satellite. And what do you notice cancels out here? What cancels out is the mass of the satellite. So it doesn't matter what the mass of the satellite is. So after we cancel that out, then the centripetal acceleration is equal to this. If we wanted to know what the centripetal acceleration was, it would equal this. We can figure out the mass of Mercury from table. We know this is 6.67 times 10 to the negative 11th for the gravitational constant, and we can also figure out the radius uh, between the satellite and the center of Mercury. But we're specifically interested in what the velocity is. Well, centripetal acceleration is equal to v squared over r. V squared over r. Well, if we do a little rearranging algebraically, multiply the r over for this equation, then we will figure out that velocity is equal to multiply over the radius. That's going to cancel out one of the radii, and then we're going to take the square root of both sides, and we will get velocity equal to the square root of the gravitational constant, the mass that the satellite is orbiting, and over the radius between the center of the large mass and the satellite. That will give you the velocity. This equation will work for any satellite orbiting a large body for velocity. That's a derived equation. So we can start plugging numbers into that to get our velocity. So we know the radius of Mercury is 2,440 kilometers. That's this. So in order to get this number, we got to add 265 to this number, which gives us 2,705 kilometers, or 2.71 times 10 to the sixth meters. We want it in meters to do our calculations. Always want to put stuff into fundamental units. So here's our radius, and we need our mass of Mercury. Well, the mass of Mercury is equal to 3.29 times 10 to the 23rd kilograms. And now we can just plug these numbers in to find our velocity. So velocity is going to be equal to 6.67 times 10 to the 11th times the mass of Mercury over the radius between the satellite and Mercury, the center of Mercury, and taking the square root. Doing these calculations, we get velocity equal to 2.85 times 10 to the third meters per second. To figure out the period, just put it into the V equals 2 pi r over t equation. And calculating for period, we would get a period of 5,970 seconds. Before you shut this off, one thing to note is you can get the period without knowing the velocity as well. You can get the period without knowing the velocity. And that comes from this equation. The fact that this equation and this equation are equal to each other. Two pi r over t is equal to gm over the square root of gm over r. If we rearrange this equation, like, for example, if we square both sides, we'd get 4 pi squared r squared over t squared equals gm over r. And if we multiplied both sides, if we cross-multiplied everything through, we get t squared equals 4 pi squared r cubed over gm. And if we took the square root of both sides, we could get t squared, the t. Again, we don't need the velocity to get the period because of this derived equation. So that's another way we could have gotten period without solving for velocity.